I'm very glad to introduce Professor Bill O'Neill from the University of Cambridge, who will be giving a lecture entitled Seeing the Light, Key Inventions that have Illuminated Our World. Please, Professor O'Neill.
Thank you so much. Thank you so much. Ken, so how many years? 2 years? This must be the most important speech in history. It's taken 2 years to write. But you end up still doing your homework on the bus, don't you? Which is what I did. But interesting to try and capture key inventions. And I asked myself the question, why am I here? Why did you ask me? What do I know about metaphysics of optics or color? I mean, I'm a laser physicist by training, and I masquerade as an engineer in Cambridge, applying the practicalities of light, generation of light, and the use of interesting things. And the conversations I've seen in the past few minutes remind me how often physicists argue. Engineers don't argue. It's either right or wrong. It works or it doesn't. But physicists, yeah, what if you did this? And you think, well, yeah, good point. You know, in my lab, it either works or it doesn't, and you just have to get on with it. So, excuse me if I do, and I love physicists, by the way. Mark had a brilliant lecture this morning which shed light on all sorts of innovations and thoughts. And if we think about the people who have been thinking about light for us, this is just a snapshot of the collection that Mark presented, but all the way back to Plato and the idea of light being shone from our eyes to illuminate the world. And then we see these incredibly important people here, the two of them I would argue, where James Clerk Maxwell did some seminal work, some work which was beyond human thought, effectively, to bring together electricity and magnetism and create this new vision, a vision that he had himself, largely. And Einstein said he stood on his shoulders in order to develop his own research on relativity. And in fact, Einstein's work on stimulated emission was responsible for the operation of a fundamental operation of the laser. And if we think about Maxwell's relationships, we see these equations which describe the propagation of an electric field, which induces a magnetic field, which induces an electric field, and this time oscillation and therefore propagation of light. I'm sorry you can't see that very well. It's brilliant on my screen. It's not very good on yours. And these equations actually are down to Oliver Heaviside, self-taught mathematician and physicist and electrical engineer who basically developed vector analysis, which enabled 20 of Maxwell's relationships to be converted into 4. And this is what we conceive now as Maxwell's equations, and it was Oliver Heaviside, an unstated genius. I mean, this fellow was phenomenal in terms of his analysis. He developed the coaxial cable. He developed the telegrapher's equations, which explained the reasons why the very first transatlantic cable between Europe and America didn't work, i.e. they didn't know they were propagating electromagnetic waves down a solid cable. They thought they were sending current. And so these equations were established to explain exactly why a multi-billion-dollar investment didn't work. So there are many people behind the Maxwell's relationships, but his conceptual thoughts have created everything that we can apply. And I'm going to change the rules. You spent the morning talking about color. What I want to do is talk about frequency, because engineers want to measure something, and we measure frequencies. And whatever color it is, I don't care. Then when you're a physicist, you talk about wavelength, and you forget about the frequency. But ultimately, the spectrum of light is broad, and it goes very, very, very long, 10 to the 7 hertz for radio, all the way to very, very, very high frequency, 10 to the 27, when we talk about subatomic electromagnetic emissions. And this whole process is divided by engineers into, or maybe physicists if they can agree, on these zones of frequency and therefore application maybe, or scale, or color, or anything else, or energy. So the photon and its energy is the important thing in which we apply as engineers or engineering scientists, because we have both engineering scientists at Oxford and Cambridge and other universities. People who try and apply the science need to understand, what are we going to do with the light? What's its use? How can I generate it? How can I apply it? What can I make from it? And fundamentally, it's all down to this distribution of different characteristics which we can cite and measure and generate and apply. I would argue one of the key inventions was the radio. electromagnetic transmission of information using electrical systems propagating through the ether, through the air, at the speed of light, at frequencies of 10 to the 3, 10 to the 6 hertz. By the way, it was Hertz that validated Maxwell's relationships. Helmholtz, his supervisor, advised him to do it. Sorry, I've got... See, I drive Macs. They're really good. There we go. Marconi, there were other people working on radio development, but Marconi first developed the commercial concept or the physical concept of the wireless telegraph in the 1890s. And this is on the back of all of the people who invested money joining cities together with wires. The telegraph companies, the telephone companies, who basically said, oh, this is a rubbish idea, there's no way this will ever work. The concept of wireless communications, never. Never trust someone who says never. Lord Kelvin said never, has no future. Of course, you're protecting your investments, so you get the biggest names you can, you sidle up to them, and you say, just tell them it's not going to work. Don't put the money in radio communications, man. And he also said there's nothing to discover anymore to discover in physics just before the explosion of physics in the 19th century. So we have to be very careful about what old professors tell you. It doesn't always have to be the truth. And I have great respect for old professors in this audience who probably thought the same thing. But it led to the boom of communications or transmissions or the connection of people right across the world. Radio communications are the essence of a critical invention based around electromagnetic waves. What's the next one? I would argue television. We just cranked up. I'm going to keep an eye on the frequency. Okay, we're going up in frequency. To carry images, you need higher frequencies. You need to be able to load, modulate frequencies, to be able to pick up and deliver data. And I would argue that television is the next most important invention in terms of the application of light. We're converting images. The BBC, great foundation provider of television and the transmission of information, and if information is power, don't forget. We find that actually there's great competition between Baird's and Marconi's development, effectively established Marconi's 405 line television transmission systems as being the standard that they would adopt. And then we start to convey images with light. Images that shared experiences that immediately allowed to connect the world together, to bring it closer, to bring it more relevant to you wherever you are on the planet. 10 to the 11 frequency, we start to get into microwaves. Just crank up the frequency, man. That's all you have to do. And deliver the power. And what happens is not only are you just changing the frequency, you're changing the way in which this radiation reacts with matter. Because now we're able to not just oscillate electrons in circuits and shake electrons at high frequency to develop more EM radiation, we're able to shake molecules. We're able to vibrate water atoms inside materials to provide energy transfer. We're able to send satellite communication systems and propagate more data, higher data rate, higher frequency, to produce greater effects. We've kind of destroyed the world with microwave comms, don't you think? Everybody walks around Oxford like that. Yeah. Your children sit at the table like that. Your students sit in your lecture theatres like that. So I don't think we've given them the opportunity to see the light. We've given them the opportunity to hide from the light, particularly with the advent of this god-awful technology. Thank you. I'm sponsored by Apple and Nokia. So infrared, well, let's crank up the frequency once again, then suddenly things change. We get heat, we get the sensation of energy. Really, we can feel it, we don't have to see it. Radio waves will pass through your head, your house, and be caught by your aerial, but this stuff, we can feel it. We're now embodied in the presence of infrared radiation. And this is a picture of an infrared camera. I mean, for those of you who's used infrared cameras in the old days, you used to have a liquid nitrogen dewar and a sensitive bolometer that could feel and measure and grade the heat. Now we have these fabulous microbolometers, silicon chip systems which can measure heat, radiation coming from whatever the source is. And this is a picture of my beehives. I've got a little thing that I stick on the back of my iPhone, which I think is a really good thing in this application, and because I can then see where my bees are. I can see through things with infrared radiation. I can gather more information simply because of its frequency change or wavelength change. Your remote control has propagated information via infrared. Heat lamps are things you shouldn't have on your patio, particularly if it's very cold, because it's not very environmental, are very useful things. You can buy these from Amazon, just by the way. Convey heat. Heat-seeking missiles are very effective when they're pointed at the right particular target. So we can see infrared, much maligned. William Herschel's experiments, and Mark, you mentioned, I think it was Mark talked earlier about who recorded the first or discovered infrared radiation. Herschel's experiment, who was the German-British astronomer who polished his own optics and made his own telescopes and discovered whole galaxies, outbeaten by his sister, of course. Discovered it simply by having a thermometer out, tried to repeat Newton's experiments and had a thermometer and realized that there was a measure, temperature, energy had been transferred through white light, through the spectrum, and he was able to pick it up. So, and I guess there are many people who've discovered stuff but not recorded it or had it cited, but infrared radiation is given us lots of activities. What about the visible? Well, we all know this is what we've been talking about all day. Light, visible light, red light, green light, blue light, magenta, or not. Where's Olaf? Or not. How red is red? Man, that's a really red jacket. Yeah, okay, it's red. What we've been targeting to try and allow people to go beyond the space of darkness is artificial light. I could have had 1 million slides on artificial light, but I've kept it down to one. Because we've got candles. Who invented the candle? Well, the first person who was able to produce fire and set light to his beehive. I mean, that's probably one example. The incandescent lamp, who invented that? These people argued all the time as to who was the inventor. This is where engineers really turn science nasty because they start to patent things. And they have fights, and they have secrets, and they have spies, and they have, I invented, no you didn't. So you have people thieving from laboratory to laboratory. And this is really because of the importance of providing people with artificial light. Everybody wants more light. You don't want to have to wait for the darkness to go. I was in Sweden last week, and you know it's now nearly northern Sweden near the Arctic Circle, and it's light all the time. It's great, but it's pretty bloody miserable in the dark in the winter when there is no light. And so this technology is critical to mankind. And we moved on from incandescent light bulbs, boo. They're quite nice light, though. The feel of an incandescent bulb on your skin and your eyes is just calming. The sharpness and intensity of a diode, ugh, my wife hates them, and yet she's supposed to be an environmentalist. And I argue, you know, there's a diode, LED technology is a very critical form of innovation, and you know, this is an important area. Many Nobel Prizes have been won because of the light-emitting diodes. And we'll see them improve in efficiency. Maxim, by the way, is also claimed to be developing light bulbs. He invented the machine gun, the Maxim machine gun. So he was a pretty broad inventor. Visible light's still part of our world, clearly. It lights us, it shines, it provides life. And the history of the solar cell goes back, you know, down to 1839 when Becquerel discovered the photovoltaic effect. And then we have Smith, who basically started to look at electrified lighting and capturing systems. Charles Fritz produced the first solar panel on a roof of a building. That powered the building. And it was really some of the work done by Russell Ohl and creates the first solar cell. And we now see this stuff spreading like a rash over the countryside. Now we get 1 kilowatt per square meter of sunlight on the Earth, in the equator. Okay, up here, a little bit less. But 1 kilowatt per square meter is a lot of power. If you think about how much power we're given by the grace of the sun and the nuclear fusion that goes on in space, and this sort of thing is really an critical technology. They're not very efficient, 12, 14%. They should be 90%, 100%, or, you know, let's not lose too much. Be like a leaf, really efficient. And maybe that's some of the technology we have to develop. Another thing that light has helped us with capturing images, capturing data. And the history of photography goes back a long way. When we start to get camera obscure in 1685 and all the way through to silver halide plates and digital technology emanating in the 1990s, and for allowing us to capture images like this gentleman's doing right in the middle of the audience now. What are you going to do with it? So I don't mean your picture, but I meant all of the images that we capture stay in the silicon chip somewhere and get thrown away when the phone's gone, or get lost in data piles, and we don't have photographs anymore. I think we should ban digital outputs and just go straight back to silver halide films. At least we'll have a history to look after when the world blows up. Critical technology. Holography. Amplitude, not forget the amplitude of the light, but let's capture the amplitude and the phase. Start to be clever with light, where we've been able to manipulate radiation. And this is the amazing thing. Why question you paying 400, 500 pounds to go and see ABBA who aren't there? Well, you would, wouldn't you? How many physicists are in the room? Would you pay 500 pounds to see a real-life hologram of ABBA? No?
It's not a hologram anyway.
No, it's a projection of multiple systems of projections. But holograms themselves will become a very critical technology position that many, many spin-outs are starting to capture the way in which we can see and convey and interact with 3D information in terms of time, amplitude, and phase, of course. Ultraviolet, well, as we start to increase the frequency, we're increasing the energy of the photon, we're increasing the ability to interact with materials, particularly biomedical materials. So we find ultraviolet radiation applied in all sorts of ways, not just to change the color of your skin, which is a very bad thing, but to look at bacterial identification, fluorescent imaging, fluorochemistry, analysis of a whole host of biomedical technologies, which have really given us the opportunity to look more closely at the bioworld, not just cure ink and have some white fillings put in your mouth, but that's another really good application. And if we increase the frequency once more, we go to X-rays, and we see some of the technologies that have been developed because of X-rays, having really high frequencies, really high photon energies, which can pass through materials which would otherwise capture electromagnetic radiation. And this is the very first X-ray photograph taken by Huygens' wife, showing a ring on her finger, and clearly not aware of the health and safety aspects of X-rays, which we've come to learn the hard way as we've used this technology. But it's a critical application in a whole host of industries, not just taking X-rays for medical diagnosis. Electronic inspection, food security, checking what's inside vehicles, understanding the nature of the structure of drugs, of proteins through X-ray diffraction, and a whole host of ways that we've used this incredible, powerful electromagnetic wave to provide information. I'm going to dwell a little bit on the laser because A, that's my field, and lasers are really important across the spectrum. We're not just targeting one particular region. We can look at excimer lasers, neodymium YAG lasers, all the way to the molecular lasers, the CO2 lasers. Why are we interested in this form of electromagnetic radiation or light? Because it's coherent, i.e., it's in phase. All the waves are traveling like one big dance, which is good. It means that I can manipulate the radiation far more easily. It's directional. I can identify and target a color. I can pick off any one of these frequencies that we can oscillate, and I can focus it because it's coherent and it's directional to a very, very, very small spot. So I can produce a very, very, very intense reaction on the thing that I'm trying to change, and I can control the temporal emission of it. An array of amazing people, starting with Einstein, who postulated the principle of stimulated emission, which we'll talk about very briefly. But the fact that there are so many physicists in the room, I'll probably skip those slides. I might dwell on one or two. Basov, this is Nikolai Basov. And what was really interesting is that Towns, an American, and Prokhorov, a Russian, were really good friends at the height of the Cold War and spent time in Cambridge at the Faraday Society talking about microwave amplification of stimulated emission of radiation, talking about really dangerous technology in the middle of the Cold War. Unbelievable. Why? Because people didn't really know what they were doing anyway. And no one had any reason to suggest that they were doing dangerous stuff. The word laser wasn't bandied around cinemas or James Bond movies at that point. It was just stuff they were doing in the 1950s, the freedom to discuss and debate. And that's something I think we're losing, unfortunately. So, laser physics. We talked about the Bohr atom, I think. Claudia, you had a nice shot, better than this, about I want to get my light to interact with matter and promote an energy state from E1 to E2. So we talked about having billiard balls or something like this. Engineers like billiard balls. Forget this probability of oscillation theory, you know. Engineers like to see this thing go, oh, it's been promoted, great. And I've got a spontaneous emission. Nature allows material to emit whatever, whenever, in whichever direction. Einstein postulated that stimulated emission can be forced, and its direction can be controlled. And so if I've got this populated energy level, and I've got this incident photon, which just happens to have the same energy or frequency equivalent to the separation between the two levels, then I can get this photon here to actually stimulate the emission of this energy state. And so when I get one, I get two. Cool. I've got two photons moving down in space. If I maintain this inversion, I can have 4, 8, 16, 32, and within a very short space of time, millions of photons all traveling in the same direction, the same frequency, in phase. That's the power of the laser, and that's why I'd argue it is the most important invention in our history. If you want to know how it works, it's very simple. To engineer it, we have this inverted material. It could be a gallium arsenide, it could be a gas, it could be a dye liquid, it could be a glass, it could be jam. You can make jam lasers if you really put your mind to it. A jam laser, imagine that. This is the challenge I give to my students, and go and make a laser out of something really cool, which no one will believe, but anyway. What lasers are a story of intensities, because I like to point my laser. I stopped working on laser inventions or laser generation because it was the kind of interesting bit, but it wasn't as cool as using the laser and pointing it at something and seeing what happens and how the material changes. And so if we look at the story of laser development right from the 1960s, where Mayman invented the first ruby laser, we've always wanted more power, man, more power, more intensity. And this chase for focused intensity has gone on for decades ever since the invention. And we've got clever tricks like Q switching, mode locking, and this thing happened, chirped pulsed amplification, which got the Nobel Prize in 2018. It's a long time before it was invented and the Nobel Prize was given. And this dramatically improved our ability to produce huge bursts of light in very, very short pulses, because power, energy, pulse length. The shorter the pulse, the more power. The power density is so high that what we really want to do to get more power intensity or density is to reduce the pulse width. And we're now down to 10 to the minus 18 of a second, okay, an attosecond. Olaf, we talked about this at lunchtime. And this is an amazing technology which we use as frequency and dispersion and coherence combined to produce a burst of light so short, it's the shortest thing in the universe, unless Claudia can tell me different. So we're creating artificial light sources in the labs routinely. And it's really transformed the way we as mankind can manipulate light. If we look about excimer lasers, why are they so critical? Well, they're just, I did my PhD on excimer lasers, and they're just really nasty UV lamps. But they're really short wavelength, and they can be really effective in creating silicon chips and using EUV lithography to have this big old mask that represents the layer of a silicon chip, flash it with UV light. We image it with a lens, and a lens, by the way, costs about £12 million and is stacked about 2 meters tall and has 30 elements, but gives you a beautiful image on your chip so you can make a circuit layer, imprint it in the pattern of your silicon, and carry on to the next layer. And then produce lots and lots of chips with very high density. I've got the 5-minute warning. We can go even further by having EUV lithography, where we're now having 13.5 nanometer radiation to get chips which have node sizes of 5 nanometers. These are the latest chips. This is the ones all the big powerhouse companies like Apple, M chips, M1, M2, are 5 nanometer gates. This is 50 atoms wide. We're using light to manipulate matter at a scale which is approaching the quantum level. The next thing is the diode laser, a very innocuous little laser made up of a tiny piece of gallium arsenide, which allows us to send a little bit of light, but couple a diode laser with a fiber optic, and you have the internet. And so over a period of 10 years in the 1990s, this technology was developed in unison to produce the internet. You did not have any idea how that internet was going to change the world. No one did. And yet the technology is delivered routinely with companies at a large scale, and we're able to produce an information age which is just beyond belief. And they're so cheap to make because of the previous technology, the semiconductor wafer production, that they're applied in practically every single part of our world. They convey light, they convey information, and more importantly, they convey energy. We talk about color. What we talk about is energy. How can I harness it, manipulate it, and promote it? The fiber lasers, which are basically, if I take a diode, a doped piece of fiber, like a terbium doping silica fiber, I can produce a fiber laser. The most efficient laser in the world, with a 100,000 hour lifetime. How many technologies do you know when you sign up and you pay on the dot, they're going to give you a 100,000 hour lifetime guarantee? That's because the stability of these technologies has been driven by the comms industry, who won't put anything in the ground unless you can guarantee it for 25 years. And so we've got a level of technology now which is just huge in terms of its application. It's transformed manufacturing industries. It's cheap, it's robust, it's easy to make, and it's just amazed everybody in the engineering space. We can do all sorts of processes with these lasers. We can do cutting, and every car on the planet is laser welded. Every cardboard box is processed by a laser. Every product you buy is processed in some way by a laser. This laser. Your iPhone has 200 manufacturing operations to make the phone and the box it comes in. And all of the other things has just astonished everybody. And so this quiet, hidden revolution in engineering has gone unnoticed by normal people. All we've done is made you more demanding in terms of consumers. You are insatiable in terms of trying to meet your desire. Your need for change, your need for renewal has been driven by the ease with which things can be manufactured. I'm not sure that's a good thing. Well, my children think it's a great thing. I don't have time for this video. It's about 2 minutes. Can I? Okay, so I'm going to put this on my website, come and take it. But this is an example of some of the fascinating processes that we can develop with lasers in industry, routinely, day in, day out, with robots. Oops, lasers in defense were an auto given. That's another video. But you can just tap that into the internet. You'll find all sorts of things. But where are we going with our light? Well, with our light, what we're trying to do is to go even more intense. We want to get to petawatt class lasers. I don't want to be mucking about down here in microseconds and nanoseconds, picoseconds. I want to be up here, man, 10 to the 27. I want to change matter. I want to have star-like capabilities with high lasers. Everyone is chasing this dream. Every continent has a bunch of extreme light sources, which are over 100 gigawatts in terms of power, and they're all over the world. And the race is on to produce the best. And the Chinese are winning at the moment. This is an amazing laser it's called the Shanghai Super Intense Ultra Fast Laser. It uses that chirp pulse amplification, which won the Nobel Prize in 2018, by squeezing light and doing things to light that nature doesn't do. That's what I found really cool. You squeeze the light by using clever tricks of optics, classical optics, by the way. What do you do if you've got one of these lasers? Well, actually, there are lots of applications of intense light burst, and it's mainly medical, transmuting radiation, nuclear waste, cleaning nuclear waste. That's a big application that people are chasing now. And nuclear fusion. We make nuclear fusion easier We don't have to spend 50 years promising. But this, one of my final slides, I think, this is a really, I don't know whether it's a cool idea or a stupid idea, but we had a meeting with this team just before the pandemic about how we could help them engineer this trip to the nearest star using a laser beam that's going to push this sail, and on the center of it is going to be this grain of sand-sized chip with a camera and a communication system and a transmission system that the sail will be pushed for 20 years through the universe, heading towards our nearest star, Alpha Centauri, and it's going to fly by at half the speed of light. And it's going to take a photo, and it's going to send that photo back, and that will test your theory, gentlemen. It's going to send that information back, and if it comes back in 40 years, we have a picture of a planet in the Goldilocks zone with an alien going. It's a 40-year experiment. Let's do it, and they're doing it. This is a real company with real money who are looking for people who will help them. And so it's an astonishing thing that lasers can do. We don't have to wait for information to come from the universe. We can give the universe information. And we can give the universe light it hasn't had before. That's really impressive. And I think, hopefully I've given you a sense of the importance of light, not just its color or other things, but for us as humans, it not just supports life in ourselves, it supports products that we rely upon to have a quality of life. It powers the information and transfers stuff around the world, whether for good or for bad. I'm on the fence, really. But it transforms materials, changes materials, it conditions materials. It does things, it helps us keep safe. Lasers cannot be used to attack people, not allowed in the Geneva Convention. But I can defend myself with them, and that's a multi-billion-dollar business now. They've been around far longer than you think in secret and helping keep people secure. But they're unlocking new science because we're able to probe matter and perhaps the universe and see what is it, how can we test our theories and examples of the world, and this new extreme light sources are creating new tools that we just simply could have dreamt of years ago. And what limits our use of light is your imagination. That's it. Thank you very much. Sorry, I overrun.
Thank you, Professor O'Neill, for that very, shall I say, stimulating talk.
Thank you.
All right. I'm glad one person or two people got that joke. If you have a question, make sure that you raise your hand so that we can get the microphone to you, so that folks online can hear what your question is. The first question over here.
About 25 kilometers down the road from here, there's Culham, where they've been working on nuclear fusion longer than my lifetime, to go back. And they use the tokamak, basically.
Yep.
And this is now all moving over to Toulouse area. I think the project's called ITER or something like that. There is a rival technology using lasers. How's that coming along now compared with the tokamak idea? That's number one question. The other thing is, with these very short pulses, I guess you can measure the topography of the moon quite accurately. I think Galileo just said it was round originally, then put a telescope on it, you could see bumps all very much against what the Pope said should be allowed. So how's that going now?
Well, thank you. That's a very interesting question. There's always been the competition between inertial confinement using magnets and plasmas and inertial confinement using lasers, where you just vaporize a target, the vapor compresses the deuterium, the fuel, and has a burst of radiation. I think the Americans have been leading the way in that sense since the 50s, really, since the thought of lasers, late 50s, early 60s, when masers were considered. It's incredibly energy intensive, and on both cases. The lasers have been promised for 40 years and they've not done a very good job because they just get bigger and bigger and bigger. But the fact now that we can produce intensity through pulse compression means one could argue that we could look for desktop laser fusion generators rather than labs the size of football fields all stacked together, because you need big chain amplifiers to have longer pulses give higher energy. I think probably tokamak's going to win out in the near term. The laser systems will probably have a good go. There's a new company being set up to look at using short pulse laser evaporation systems with Thales, which is the French engineering company. So the game's not over, basically, but I think tokamaks are winning out at the moment. The distance to the moon? I don't know that much about the metrology aspects of ultra-short pulses. I think we can get decent measurements in place using topographic systems, but I don't know. I don't know the answer. It's changing anyway, isn't it? It's bouncing, it's oscillating. It's bouncing, yeah. Yeah. This is a relaxation of being caught by the Earth's gravitational pull, apparently. But to ask a physicist, they won't disagree with me. Maybe they will.
Next question in the front.
Thanks. That was absolutely delightful. We'll need to talk about the difference between engineers and physicists and philosophers a bit later. That's going to be fun. But meantime, you say something about the future of medical applications of light.
Yeah.
I kind of expected that, but you can't do everything. But I think that's really opening up. So phototherapies and so
Phototherapies, photodynamic therapies have been around for 20, 30 years, where selected tumors, for instance, are targeted by a drug which only absorb a particular radiation, and you shine light through your abdomen, for instance, to attack the tumors. Loading gold nanoparticles into tumors which resonate with infrared radiation, produce heating, local heating. There are lots of techniques which can be applied. Laser surgery, of course, has been around since the 60s. In fact, the first laser application was retinal detachment, to reattach retinas using ruby lasers. So lasers and biophotonics, if we want to call it that, is a very strong and growing field. And I'm sorry I didn't capture that in the slides. But yeah, I think we're seeing more and more developmental procedures being controlled by not just high-intensity coherent light, but just light in general. Phototherapy, which we thought of as being a thing, is actually a real practicing set of procedures.
Great. And the next question next to him.
I was going to ask you about the white photon.
The white photon.
No, sorry,
Olaf.
just a joke.
The white photon. Well,
No, sorry.
Let me just
Forget it.
I'm going to finish.
Okay, sorry.
I'm going to finish.
Too late. Okay, the white
late.
photon.
The interesting thing about the white photon concept is that in order to get chirp pulse amplification, in order for you to actually, how do you produce a short burst of light? You just have a gate valve and flick it and turn it on and off. Do you have a current which basically pulses to the go button is a very short current pulse? When the shortest current pulse you can get is kind of picoseconds, if you're lucky. So you need to develop optical ways of generating bursts of light, and that's to have a very, very broad amplifier which amplifies so many frequencies in that laser cavity. So many frequencies are amplified, so they have standing waves in the cavity, and at some point they all align to produce a burst, a phase-matching burst of light, and that burst of light is inversely proportional to the spectrum of the amplifier. So one could argue we're generating white light because we're generating every frequency in an ultra-fast amplifier, which just happens to recombine for that moment in space and time to produce the shortest burst of light. The wider the frequency range, the shorter the pulse. And so it's kind of almost there. And Olaf, I think your research is going to produce some really interesting findings. We talked to the single photon producers, the quantum computers. Didn't mention quantum computers. That's for another conference. But that single broad spectrum amplification is where you'd probably find your white photon.
Okay, thank you. I didn't think you wanted to talk about.
I didn't, but no, you got me going.
No, sorry, can I get back to, you showed the Maxwell's waves going up and down, which we saw more or less on there.
Yeah.
And I just have a question. We're always told the electric field causes the magnetic field, and the magnetic field stimulates the electric field. But if you got circular polarization, it's actually the opposite.
It just
because
goes
you got
round.
the electric field.
Circular polarization just has your whole system.
I know, but in that
around.
case, the electric field decreases the magnetic field.
Yeah.
So,
Yeah.
but from the equations, doesn't it tell us that the one increases the other? So how can you get one to decrease it? Because in a sense, when it's going around in a circle, the electric field goes up and the magnetic field has to decrease.
Well, you have them, the phase changes, doesn't it?
Yeah.
So, and that's generally driven by the material that sources your polarization.
Okay.
Your polarizer does that, for instance. Mark, where's Mark? Talked about, linear material polarizers. You can polarize through reflection. You can polarize through, using Brewster angles. And often the light sources that we use, lasers are very rarely polarized. It's really difficult to polarize a cavity, an axisymmetric cylindrical cavity in anything, because your radiation is in all directions. It's polarized in all directions. It's got unpolarized. To circularly polarize light, what we do is we put it through a mirror, which automatically selects the polarization, retards one axis and accelerates the other, and so you can control polarization that way. Or you pass it through a Brewster window. And Brewster was mentioned in Mark's talk, who did the early work on polarization, and we use Brewster window selection to be able to get horizontal polarizing or vertical polarizing, because we can use the transmissive component rather than the reflective component. But the whole concept of polarizing light for us is really important, because it means we can manipulate the beam once we've created it. We can change its direction. We can select a particular part of it in terms of power or amplitude, and we can make it absorb more in materials. At the end of the day, the lasers that produce have to do something, and we want to maximize that, and we'll do whatever we have to do to the system to be able to maximize it. And polarization is really important. Yeah, thank you.
We have a question in the back. If you could hand it over here, please. No, we need to wait for the microphone so the folks online can hear. Thank you.
Hi, I asked the question because I'm a local resident.
Okay.
You mentioned the laser, name I've forgotten.
Sorry, could
you mentioned the laser at AWE.
Yes.
AWE is atomic weapons.
Yes.
I live near there. And so are they using lasers in a military application?
Why would an organization like AWE want a massive laser? It's basically...
That's my question.
Well, if you want to explore the impact that extreme and physical environments have on materials, then what you do is you have a target, you make a target, you stick it in front of the beam, and you whack it with as much power as you can, and you watch what happens. And you can stimulate intense bursts of energy, nuclear explosions, by intense bursts of light. And we've already done experiments where, on the very, very micro scale, with a beam focused to a few tens of microns, half the width of your hair, we can get the same physics replicated that you could from detonating a hydrogen bomb on an atoll. And so energy delivered in a very small point in space and time on a specific material, whatever that material is, can provide you with simulations, real-world kind of replicas of things you can't do in real life. Test nuclear bombs, or test the effects of radiation, physical particles, gamma bursts, all sorts of things we can generate in the lab using these really short burst pulse lasers. The EWE one is the Orion facility is a new laser, and probably about 20 years old in the making. It's about a tenth of the power of the ones the Americans have in California, but the Americans are so expensive to do tests that the guys in EWE are picking up quite a lot of experiments that could be done on lower cost systems. So you really want to use these energy deliverers to replicate scenarios you can't do in the real world, but you want information about, for instance. Does that answer your question? Yeah, okay, thank you. Exactly, yes, that's the short answer. Yep. Yeah.
The next question is over here.
Thank you. Thank you for a fascinating lecture. I was interested, you talked about the Russians and the Americans when they worked together on things. And earlier on, you talked about Marconi. and how he invented radio transmitter. But of course, the person who did most of the engineering work was Fleming of the right-hand rule. But Fleming had signed a contract with Marconi that he wasn't allowed to say that he'd done it.
Yeah.
And so Fleming has been forgotten in that, just used for schoolboys or
That's
school
right.
pupils. To
Yeah, but
use
really
his name.
important, really important rule, right?
Yeah.
Yeah.
So what I'm interested in is this relationship between the academic and the commercial, and then you've been talking about the defense world as well.
Yeah.
And how that interacts, and how does it hinder, does it help? Any views that you might have on those relationships between pure exploration and people making money, or people wanting to spend money on defense?
Absolutely. I have very strong views. I think if you, well, it's very interesting in the UK, let's say the UK university R&D space, is that if you invent something as a research scientist, you can either publish or you can hold back and license and patent. And universities are encouraged to do impact and to be measured by their impact, not in terms of number of papers or number of citations or the greatness of the work, but on the economic value of the work that you do. And if you patent, then you lock out the world from that knowledge. And if you patent, you actually restrict the growth of enterprise, because you lock out everybody else from developing comparative systems, for instance, whatever the application might be, for 20 years. I've had patents that I've had in the past that have restricted the growth of commercial technology. I'm not proud of that now, I don't think. Patents are there particularly to make money, ultimately, and to defend your space. I think it would be better, for instance, if we didn't have patents and we allowed free determination of information and publication. Because modern students, particularly some of the ones that I know, who are very keen to have a business, to have a spin-out, to do all the things that Oxford and Cambridge and other universities are great and good at, is the entrepreneurial side of life actually kind of puts blinkers on us and restricts knowledge transfer and sharing. It's always been like that. Edison, Swan, and beyond. Patents are not a new thing. They've been around forever. They just leave a bit of a bad taste in your mouth, that's all.
We've got about 8 minutes now where we have where we can ask questions either of Professor O'Neill or Professor Marastone. So if any of you had questions for Professor Marastone and you weren't able to ask them, we also have an opportunity to do that now as well. Please, right here.
So I was going to ask a banal colour-related question. So white LEDs, I assume, are not actually white in terms of what they're actually emitting. What frequencies do they emit, and do they vary?
White LEDs, well, they can either be generated by having infrared LEDs hitting a phosphorus emitter, so you get a phosphorescence or a fluorescence, or they can be tuned RGB emitters, which are collected together under a glass bulb. It looks white. Is it the colour, or is it your perception of colour? That goes back to the morning session, really. What's colour? I don't really care, I just want the frequency. I can measure frequency, and its intensity, and its relevance. But white LEDs are really coming on in leaps and bounds, actually.
Yeah, I was recently at a concert where they had white LED spotlights. They're really intense lights.
There is also the thing called the continuum laser, which is a laser which produces emission at all wavelengths, so it looks white. It's not a white photon, because there are lots of multicolored photons being generated, and the continuum output is a white source. It's very, very intense, and it's used for biomedical applications largely. And you can select the particular frequency you want from it. White light, yeah.
A question from Professor Marastone.
You mentioned that there is a plan to travel to the closest star, to Proxima Centauri, I presume. So but why would you like to go there?
Why would I like to go there? It's not me.
Not you, but in the sense that the ideal target would be...
Because there's a planet there in the Goldilocks
in
zone.
the Goldilocks, okay.
So it's looking for extraterrestrial life.
That's it, okay.
On a tiny little chip with a material they haven't even got a clue what. It's got to be so light it doesn't drag this little grain of sand down. It's got to be deployable. It's got to be sufficiently technological that it can withstand gigawatts of light shining at it from the ground with an array of lasers, not just one laser, all targeted like a ground station where all the discs come up. It's got to be deployed in the outer regions of the atmosphere, 200 or 300 kilometers, where it's not going to be dragged by the atmosphere, and then deployed, and then fired, and then it's got to spend 40 years or 20 years going out there, and then 20 years sending the information back to the same ground station, apparently. So this has been thought out. This is not madness.
No.
Why? I don't know.
No, for the extra,
I don't have
for the
$100
planet is
million
good.
to waste on even thinking about it, and it's costing $100 million to think about it.
Good. And related to this, there are plans to build a radio telescope on the moon. It would solve a huge amount of problems that we have on Earth, and it could be sizable, unlike the Hubble Space Telescope or the James Webb.
Yeah.
Could your technologies, that type of technology you describe, involved in these plans?
Into making stuff on the moon?
Yes.
Well, I guess lasers have been employed. Solar-powered lasers have been employed up in space to do things. There's plenty of light in space, actually. So if you can use your silicon cells to convert light into electrical power, you can drive lasers pretty much anywhere. The moon's a really good material for 3D printers. So you can get a kind of pseudo-metallic material from moon dust, and NASA's already done experiments on building stuff with lasers on Earth for applications on the moon where it's abundant, the material. But companies like SpaceX are planning on launching, allegedly, 2 rockets a day by 2025 that can carry 100 people each. So the population of these bases is the likelihood is going to increase quickly. You might get your wish to go into the universe that you spent so long looking up at, where you can be in it.
In the green shirt.
Sorry, just a very quick question. You did show numbers in some of the slides for the efficiency of various lasers with time.
Yeah.
So just out of interest, the Project Starshot firing a sensor at Alpha Centauri.
Yeah.
If you want gigawatts of big laser, what's the upfront energy cost for the rest of us?
Yeah. Well, you're going to have to build a couple of power stations next door to it. We're going to have to collect the power from the whole of America, probably, and tap it into this particular footprint. Gigawatts of power, 100 gigawatts is the argument. How many megawatt power stations is that? A lot. So power is the big problem. And again, there are many problems which are not necessarily insurmountable, but they're certainly, for a brief moment in time, you might take all of the power of, half of America's electrically emitted power for a second a day, pulsing it, keeping it moving, using photon pressure to push the sail. But you're right. See, ne'er-do-wells like you just kill ideas completely. You should, where can I get the power? Not how am I going to get the power? But no, it's a very good question.
Would it not be more efficient to put that in?
Could you use the microphone, please?
Would it not be more efficient to put that in orbit, the laser that pushes it to Alpha Centauri?
Yeah, if you could collect, if you had big enough solar panels to collect the light to be able to fire and produce the beam. I mean, we've got lots of electricity in space.
I just mean to get rid of the atmosphere.
Yes, there is definitely a problem of atmospheric propagation, yeah.
Great.
I mean, what we're starting to see now is visible comms. We talked about communication from radio, microwave, etc. A lot of the interest in space now is laser-based comms, cranking up the frequency even more, because microwave radiation, the frequencies means data rates are very low. What you want is optical frequencies and optical communications, which require line of sight and atmospheric disturbances to be massively minimized or eliminated. I think, if you get to the point where you can produce solar collectors on the moon, then you've got a much greater chance of having these systems.
Is this Alpha Centauri laser?
That's basically a terbium laser, so it's running at sort of 1 micron wavelengths. So
Which color is that?
Sorry?
Infrared, okay.
Yeah, it's infrared. So it's in that sort of frequency range. And it's just under 1 micron. And it's 65% efficient, which is pretty efficient. The first laser was 0.01% efficient. So it's 4 times more efficient than solar panels. So it's not the rate limiting technology.
Let's thank Professor O'Neill again.
Thank you very much. It was a pleasure. Thank you.